When a ground fault circuit interrupter, or GFCI, is installed on a branch circuit, it monitors the current flowing through the hot and neutral conductors on that circuit. If it detects an imbalance in current, such as an excessive amount of current flowing to ground, it trips and breaks the circuit. The grounding conductors for the GFCI and the non-GFCI receptacles are all tied together. This creates a conductive path for any leakage current that may occur. When leakage current flows from the load side of a non-GFCI receptacle to ground, it also flows through the grounding conductor to the GFCI. The GFCI detects this leakage current as an imbalance between the hot and neutral conductors on its own load side. The GFCI trips and breaks the circuit, interrupting the leakage current and providing protection to all receptacles on the branch circuit. The protection provided by GFCIs is not absolute. It only detects leakage current that flows through the grounding conductor. If leakage current finds another path to ground, such as through metal conduit, the GFCI may not trip. It is important to ensure that the grounding system is properly installed and maintained for GFCIs to provide effective protection. The maximum number of receptacles that can be protected by a single GFCI varies depending on the GFCI's rating and the load it is serving. GFCIs are required in specific areas in residential and commercial buildings such as bathrooms, kitchens, and outdoor areas. A ground fault circuit interrupter, or GFCI, is an important safety device designed to protect people from electrical shock. It works by monitoring the current flowing in a circuit and quickly interrupting the power if it detects a ground fault. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. This can happen if someone touches a live wire or if there is a fault in an appliance. GFCIs are designed to detect even small ground faults as low as 5 mA and trip the circuit within a fraction of a second. This rapid response time can prevent serious injury or death. The basic principle behind GFCI operation is the comparison of current between the hot and neutral conductors. In a properly functioning circuit, the current flowing through the hot conductor should be equal to the current returning through the neutral conductor. However, if a ground fault occurs, some of the current will flow through the ground path instead of returning through the neutral conductor. This creates an imbalance between the hot and neutral currents. The GFCI constantly monitors this current balance using a differential transformer. This transformer has two windings, one connected to the hot conductor and the other to the neutral conductor. If the currents in the two windings are equal, the magnetic fields they produce cancel each other out. However, if there is a current imbalance due to ground fault, the magnetic fields will not cancel, and a voltage will be induced in the third winding connected to a sensing circuit. This voltage triggers the GFCI to trip, interrupting the circuit. The tripping mechanism in a GFCI typically involves a solenoid or relay that physically breaks the circuit. When the sensing circuit detects a ground fault, it sends a signal to the solenoid or relay, which then opens the circuit contacts, cutting off the power supply. GFCIs are designed to be self-testing. Many GFCIs have a test button that allows users to verify that the device is functioning correctly. When the test button is pressed, it creates a simulated ground fault, which should cause the GFCI to trip. If the GFCI does not trip when the test button is pressed, it indicates that the device is not working properly and should be replaced. There are two main types of GFCIs: receptacle type GFCIs and circuit breaker type GFCIs. Receptacle type GFCIs are designed to be installed in place of standard electrical outlets. They provide ground fault protection at the point of use. Circuit breaker type GFCIs are installed in the electrical panel and provide ground fault protection for the entire circuit. GFCIs are required in specific locations by electrical codes to provide enhanced safety in areas where there is a higher risk of electrical shock. These locations typically include bathrooms, kitchens, outdoor areas, garages, and unfinished basements. The specific requirements may vary depending on the local electrical code. Firstly, bathrooms GFCIs are required in bathrooms to protect against electrical shock hazards associated with water and electrical appliances. Secondly, kitchens GFCIs are required in kitchens to protect against electrical shock hazards associated with water cooking appliances, and other electrical devices. Thirdly, outdoor areas. GFCIs are required in outdoor areas to protect against electrical shock hazards associated with wet conditions and the use of electrical tools and equipment. Fourthly, garages. GFCIs are required in garages to protect against electrical shock hazards associated with power tools, appliances, and other electrical equipment. Fifthly, unfinished basements. GFCIs are required in unfinished basements to protect against electrical shock hazards associated with damp conditions and the use of electrical tools and appliances. It is important to note that GFCIs do not protect against overloads or short circuits. They are specifically designed to protect against ground faults. Overload and short circuit protection is provided by circuit breakers or fuses. GFCIs are sensitive to moisture and can be affected by excessive humidity or water exposure. It is important to protect GFCIs from direct water contact and to ensure that they are installed in a dry location. GFCIs have a limited lifespan and may need to be replaced after a certain period of time. The lifespan of a GFCI can vary depending on the manufacturer, the quality of the device, and the environmental conditions. It is recommended to test GFCIs regularly and to replace them if they fail to trip when tested. GFCIs can be a valuable addition to any electrical system to provide enhanced safety and protection against electrical shock hazards. However, it is important to understand their limitations and to use them in conjunction with other safety measures such as proper grounding and the use of surge protectors. When a GFCI is installed in a circuit, it provides protection to all outlets downstream from it on the same circuit. This means that if a ground fault occurs at any of the downstream outlets, the GFCI will trip and interrupt the power supply to the entire circuit. This protection mechanism is based on the fact that the GFCI monitors the current flowing through the hot and neutral conductors of the entire circuit. If there is a current imbalance due to a ground fault at any point in the circuit, the GFCI will detect it and trip. To ensure that the downstream outlets are properly protected by the GFCI, it is important to wire the circuit correctly. The hot and neutral conductors must be connected to the GFCI's line terminals, and the downstream outlets must be connected to the GFCI's load terminals. Additionally, the grounding conductor must be properly connected to all outlets in the circuit. The grounding conductor provides a path for fault current to flow back to the source, which helps the GFCI to detect the ground fault and trip the circuit. If the grounding conductor is not properly connected, the GFCI may not be able to detect the ground fault, and the downstream outlets will not be protected. It is also important to note that the GFCI only provides protection against ground faults. It does not protect against overloads or short circuits. Overload and short circuit protection is provided by circuit breakers or fuses. Therefore, it is important to ensure that the circuit is properly protected by both a GFCI and a circuit breaker or fuse. The number of outlets that can be protected by a single GFCI is limited by the GFCI's rating. The rating of a GFCI is typically expressed in amps. The total load of all the outlets on the circuit must not exceed the GFCI's rating. If the total load exceeds the GFCI's rating, the GFCI may trip unnecessarily or may not provide adequate protection. It is important to consult the GFCI's instructions for specific information on the number of outlets that can be protected. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. The GFCI must be installed in a properly grounded enclosure. The hot, neutral, and grounding conductors must be connected to the correct terminals. The GFCI must be tested after installation to ensure that it is functioning properly. If you are not comfortable installing a GFCI yourself, it is best to hire a qualified electrician to do the work. Electrical work can be dangerous, and it is important to ensure that it is done safely and correctly. GFCIs are an important safety device that can help to protect people from electrical shock hazards. They are required in specific locations by electrical codes and should be installed in any area where there is a risk of water exposure. When properly installed and maintained, GFCIs can provide reliable protection against ground faults. In addition to GFCIs, there are other safety devices that can help to protect against electrical hazards. These include arc fault circuit interrupters, or SIs, and surge protectors. SIs are designed to protect against arc faults, which are caused by damaged or deteriorated wiring. Surge protectors are designed to protect against voltage surges, which can damage electronic equipment. It is important to consider all of these safety devices when designing and installing an electrical system. By using a combination of safety devices, it is possible to create a safer electrical environment. Electrical safety is a serious matter, and it is important to take all necessary precautions to protect yourself and others from electrical hazards. If you have any questions about electrical safety, it is best to consult a qualified electrician.